do you improve, is there a way to improve the Cramer-Rao bound? Remember, so what is Cramer-Rao bound? You have, generally you have variance of a unbiased estimator that's going to be greater than the, so this is generally going to be greater than or equal to the Cramer-Rao bound for theta. And as we know, the Cramer-Rao bound depends on the density function. So this is one expression, right? So you can see sometimes, of course, in some cases the variance will agree with the Cramer-Rao bound. Then this is an efficient estimator. So if it doesn't agree, the question is it because the bound is weak and can we improve the bound? That's the idea here. So is it possible to push this up, the bound, push it up here? So something needs to be added to this. Look at here. If the logic is, if you are thinking, you need to add something to it. And if you look at the Cramer-Rao bound, it depends on the, remember there's only one density. Once you have the data, you have a density function representing it, right? So you put all the x1 through xn data here. All you have is the density function. So here you take the logarithm, or the density function is the same. This is the first derivative. So the idea was, Bhattacharya's idea is, suppose we bring in the higher derivatives, is it possible to push the bound up? So let me, so we want to look at derivative of log f with respect to theta, the second derivative of log f with respect to theta, etc. And we have this tx minus theta, where this is an unbiased estimate. So I'll look at this vector. So let me call this to be y, or let me call y to be, so in the Cramer-Rao bound we only use the first one. So if you look at expected value of Tx, Tx is an unbiased estimator for theta. So one way or the other way, if we found an unbiased estimator, then the theorem says that the variance of the unbiased estimator is going to be greater than or equal to the Cramer-Rao bound. And the Cramer-Rao bound is given by the derivative of the logarithm of the density function. We also found, I'll show, so if you do this, if you take the expected value of, so let's do this quickly here. So this is expected value, means the function multiplied by density function. So we went through this several times now. So d log f is 1 over f multiplied by df by d theta. So this f cancels. So you get this to be tx minus theta multiplied by d log f by d theta. So if you write this as tx d log f, not log f, log is gone, df, right? And if I use the regularity condition, then this becomes what? Anyone? We just went through this. This derivative goes outside. So the first term becomes d by d theta of integral tx df. So that's going to be theta. Minus this derivative goes outside. Integral of f is 1. So that's 0. So this is just 1. Now I want to do this exactly the same thing but for a higher order derivative. So let me just do it here. I'm going to do it for a higher order derivative. So you can, it's more convenient to write y in terms of just the derivative of the density function itself, because ultimately that's what matters, right? I mean, both you can relate. So what I want to do is, let me, any one of this, so this is fine. So we'll use this as a motivation factor to do this quantity. So this, if I expand, is going to be Tx minus theta. Yeah, so there should be, this is what we are going to define y as. So this should, the second factor has got a 1 over f here, because I want that to cancel off. Look here, this f cancels now. Then you can see using the regularity conditions you can, so this result is now Tx dkf over d theta k minus theta goes outside dkf by. Anybody, so by repeated use of regularity condition, this goes outside. By repeated use of regularity condition is on f. So this turns out to be dk over d theta k Tx f dx minus dk over d theta k. There is a theta here, integral f dx. But this is 1, so this term is 0. So what is the answer to this? Anybody? Huh? What? That's expected value of Tx. Expected value of Tx is 0? Okay, so you have d theta over d theta to the power k. So this is not 0 always. This is 1 if k is 1 and 0 if k is greater than 1. So that's the key result. So again, I don't need any of this stuff. So you can see, if you want, you can see that all the Bhattacharya thing has done is, the first one is the same as what we wrote before, d log f by, you can, this is the easiest one, but in this second one, if you put log here, that's not the same as this. There will be more terms. So you just take the second derivative of f with respect to, so this is the same as 1 over f df by d theta, but this is not log f, just f. Alright, so that's a random vector. And to exploit this, so let me define z to be Tx minus theta and this y vector. So this will be k plus 1 by k plus 1. This is k by 1. This vector is k by 1. So this is k plus 1 by 1. So let me look at the expected value of z transpose. What is the expected value of z? Anyone? We just went through this. All the expected value of this is 0. Expected value of this is 0. For expected value of the top one is 0 because expected value of one.
First element of y is 1.
No, nothing is 1 because that's also by, remember, expected value of this is multiplied by f. F will cancel, the integral of first derivative is 0. Why is it 1? What we have shown, I think you are getting confused. What we have shown is see, this is yk, right? This is the kth entry. So what we have shown is expected value of y, look at here. Expected value of y1 is integral 1 over f df by d theta multiplied by f. F cancels. It will be df by, d by d theta of integral f, but this is 1, so that will be 0. All the y will be 0. Okay. So the covariance matrix is, the covariance matrix of the z, mean is 0, expected value of z is 0. So its covariance matrix is just z transpose. So that's going to be, you can see the first entry is expected value of tx minus theta squared. That's the covariance matrix of tx. And this is expected value of y transpose. Anybody, what will be these entries here? So this entry will be expected value of tx minus theta multiplied by the y vector. We just went through this. y1, y2, y3, what is this expected? Right. So if you look at the, what is it? Yeah, so this will be a row vector. This will be 1 and 0, 0, 0, because look at here. So if I call, let me call this to be, so this will be expected, if I call tx minus theta to be t1, this is t1 y1, expected value of t1 y2, etc. And so this is your t1, expected value of t1 y1 is 1, everything else is 0. So this will be 1, 0, 0, 0. This will be 1, 0, 0, 0. And this is a non-negative definite matrix. So the interesting thing is, let's look at what is y transpose. So again, it will be a random, that will be random variables, expected value. So that will be a non-negative definite matrix because it is random vector multiplied by transpose. So I'm going to call this the Bhattacharya matrix. What is B11? Anyone? Yeah, see, B11 is expected value of D. You can also write, because if it is I equal to 1, this is D log f by d theta the whole squared. So that's the same as J11, right? So if you want the B matrix, you can write it like this. So you have, let me rewrite this result. So you have this one turns out to be, here you have covariance of T, and you have B matrix. Here you have 1, 0, 0, you have 1, 0, 0. This is positive. So again, we can use the previous result. So this is let's call this case to be A C C B. So we can do something we did earlier. So if I multiply this, what do you get? Quickly, A minus right, CB inverse C is multiplied by this is C, right? And here 0, and this multiplied by B, right? Now let me multiply by the inverse of the transpose. So if this is S, I'm going to multiply by S transpose here. So that's I0 minus, remember C is C transpose, then B is the same as B transpose, because this is a positive definite piece, and this is I. So first row into first column, what do you get? So you just have to multiply here, I minus C inverse, C transpose B inverse, 0 I. So what do you get?
Sorry, I think for this thing to make sense, we need a transpose, like C transpose below A, right? Because C cannot be a like row and a column.
Yeah, okay, so this is C transpose.
So in the other matrix where I'm going to multiply, we just C transpose.
C.
Oh, no, on the other side. Where we have A minus C, D inverse C, that doesn't make sense. It should be the other side. The right. Like the very far right.
Okay, what is it? This one?
This guy should be
C transpose. C transpose, right? So this will be A minus C transpose B inverse C, right? And this will be C and C, and this is, this should turn out to be 0 if I multiply that correctly. Anyway, remember, this is already a non-negative definite matrix. You are right, this should be of the form CC transpose is being a positive definite matrix. So this should be, let's make sure the dimensions are right. C is a row vector. So this should be a column vector. So this should have been transposed to start with. So then only it will make sense, right? That's correct. That's what it will make sense. So then this should have been, we should be multiplying with, so when you do this, what do you get? You get, so, or I should have done is, the cleaner way is I should call this to be, then this is fine. I don't want to mess this up. Let me call this to be C transpose. So the result will turn out to be, this is correct. And so you have this quantity to be, this quantity should be non-negative definite. So I'm going to call this to be C transpose. So what, look at here, this is your A. So covariance matrix for Tx is greater than or equal to or minus C transpose. C transpose is this vector 1 0 0 0. Then you have B inverse. Then you have 1 0 0 0. So what will this operation do? Anyone? This will pick up B11, isn't it?
Why do you have covariance of T? Isn't this just variance? Because T is just one number.
No. Remember, yeah, I mean covariance and variance is the same. I mean for a, it's a scalar, right? So covariance, what I meant was variance, right? So variance of Tx, the first entry, which is this, is B11. So what's the moral of this story? Again, you can do exactly the same way. This is variance, right? So B is here. So you can show the same way that the B11, right, is greater than, you can use exactly the same procedure, 1 over 1. Remember, previously we had a J matrix. We showed that J11 is 1 over J11 is smaller than J top 11. So this is the Bhattacharya bound is, so pictorially how will it look like? The Cramer-Rao bound is here, which is 1 over J11, and B11 must be here. And your variance maybe of Tx is here. So this is a better bound compared to this, right? So again, you can do the same stunt. Just use only the second derivative. I've gone through all this here. You can do a lot, and I'm not going to proceed in the notes. You can do this. You can do a 3 by 3 matrix and see the improvement. So each time you bring in a derivative, the bound improves. And so you get, at least the second case, I think it may be useful to use in some practical problems and so on.